So ready to start with cameras. Just to remind you of all the light stuff, sort of summarize it. Starting with sunlight, this is sort of the simplest way to make light with just a hot surface, the sun. Alternatively, a piece of hot tungsten and an old-fashioned incandescent lamp. Both of them make what's called a black body spectrum. In the sun's case, that black body spectrum is really sort of the definition of white. In the case of a hot piece of tungsten, it's white, but it's not, because it's got a broad spectrum of colors, but it's not the white of the sun. It's missing a lot of blue. It's not hot enough. What else? Then I went through all the ways in which light interacts with matter, sort of the principal ways in which it interacts with matter, and we'll see these coming up again. I guess I should say with cameras is the first of a couple of topics. We're going to run out of time pretty fast, but we're going to go through, that is in the semester, a couple of topics that use light and the various tools that we've seen, the ways in which light interacts with matter. We're going to use those as tools to get things done, like to take photographs. So anyway, so back to sunlight, simplest form of light. Fluorescent or discharge lamps. Now you're building light a little more strategically. It involves using atoms to emit the light. Instead of getting them hot, hit them with projectiles, charged particles that you push electrically, and cause them to fluoresce, to emit, in this case, to emit light associated with their atomic structure, the way the electrons reside in these standing waves in the atom. And the fluorescent lamps, that's a little bit more complicated, but it's still the same idea. You get mercury to emit its atomic fluorescence lines, but then you convert that ultraviolet light into visible light with phosphors. And the fluorescent phosphors, all these fluorescent materials you've got in modern life, not in old life, ancient life, but in modern life, we use a lot of fluorescent materials just because they're pretty. They take in photons, go to excited states. So there's still atomic or atomic-like systems that have energy, that have electrons in orbitals or more broadly things like molecular orbitals or even levels in solids. And finally, they take in the energy, they squander some of it typically, and then they send out new photons that are shifted in energy down to lower energy, and therefore coming out of the ultraviolet into the visible, maybe the blue end, and maybe out of the blue end down further towards red. So that's another way to craft light. Then I looked at, with LEDs, we're looking at solids emitting light, and you strategically build the solid so that you end up with electrons that are in an excited, a band of levels that's excited, that has a lot of extra energy, like the conduction levels, and you let them drop into less energetic levels. Again, these are quantum standing waves in the valence band, and in the process emit light. So people have spent the past 30, 40, 50 years trying to engineer materials and structures out of those materials that as efficiently as possible take the energy the electrons give up in going from the conduction band to the valence band and turn that into light and turn that into the various colors that you want. It's not easy. Nature doesn't give us every possible choice of band gap, for example. You can't make any old color. It's a little bit tricky. And then lasers. The concept of the laser was that if you use a material that can amplify light, and in this case, these are still quantum systems. You're still using radiative transitions, whether they're in atoms or whether they're in solids. You got the same story, but now instead of having them emit light spontaneously, so each photon's a one-off and independent, you have them emit light in the process of amplifying an existing photon. And that then gives you multiples of the same photon, one giant wave, and you can do sort of things. You can do things with that you cannot do with conventional light, having all the photons in the same, identical. The details of lasers, it's a whole long story. Something that came up in your problem sets, but I never mentioned, is that making a system that can amplify photons is already a challenge, because it's easy to make systems that absorb light. It's harder to make them such that they not only do they not absorb light, but they actually enhance it, make it stronger. That's tricky. It has to have a power, it has to have a source of energy somehow. It has to have a way of amplifying without absorbing, which is not, yeah, okay. And ultimately, there are limited choices. And you can't, for example, as in the problem set, you can't just make a laser medium, something that's capable of amplifying light, that can amplify any old photon. It's just, you can't do this. You can get, there are systems that will amplify one very particular frequency of light, or ones that will amplify some swath of choices of frequency. But to get every old frequency in any old direction, nah, it's too hard. Those materials just don't exist. Nature doesn't give them to us. Any questions about producing light and the initial tools for manipulating it? Things that I haven't covered that you're wondering about or came up on the problem set? It's a golden opportunity. There's so few people here to hear you ask the question. You don't have to be embarrassed. All right. I'll keep talking. Okay, so cameras. So this is now we're going to start using light to do something that you care about. Whenever you're taking pictures, you now all have cameras, all your cell phones, built-in cameras, your laptops, built-in cameras. What I'm talking about is inside those, and they're astonishingly sophisticated devices, very small, but they have all these features in them. Or many of them. Ultimately, the bigger cameras, the specialized cameras can do things that your cell phone cameras can't. But, okay. So here's an opening question. You know about the sort of the existence of telephoto lenses and wide-angle lenses, presumably a little bit, like the idea. If you want to take a photograph using a camera, and you want to make some distant object big in the photograph without digital zoom. Digital zoom is, that's the computers playing games with this stuff. But it is possible with just a camera alone to sort of zoom in on some small object in the distance and make it larger. Well, what do you do to the lens of the camera? Assuming sort of the simplest of lenses, what do you do to that lens to make the object bigger? You okay with the question at least? If it doesn't, if there's you don't have any sense of the answer, we'll come back to it. But do you think, what do you make the lens bigger in diameter? You've seen people with great big lenses out there. How about make the lens smaller in diameter? Okay, so we sort of narrow it, conceptually narrow it. How about increase the curvature of the lens so it's got more like a ball rather than a flat surface? Okay, and how about decrease the curvature of the lens? Okay, a couple people. So it's pretty broadly splattered across. Increasing the diameter was probably the least popular, but we'll come back to it. Or I'll tell you the answer. You won't remember it, and we'll come back to it anyway. Oddly enough, it's D. It's decrease the curvature of the lens. You actually want to make it flatter to get it to produce a larger. To zero in on some distant object. That seems counterintuitive, but we'll see why it's the case. So things about cameras, they record an image. They record it on an image sensor. That is, they're projecting light onto an image sensor, some device that actually can map out the pattern of light that hits it. When I first started teaching this, image sensors were really rare, at least the ones that you're used to. They existed, of course, in television cameras from way back when, but film was the deal in 1991 when I started this course, and stuff's evolved now, so film is nearly dead. It's not a good time to invest in the film companies, the Kodak and all, at least not for film. The image, so they're trying to use somehow this image sensor that detects the pattern of light that hits it, and they kind of control that light. Okay, most cameras need focusing. There are disposable cameras. They're getting rare. These ones that are they used to be about $10 or something like that, and you bought them. You took the pictures actually on film, and then you turned them back in and had them developed. And they were so simple. They had no focusing. We'll see how that's possible. It turns out even your cell phone cameras have focusing. there are reasons why they need it. Okay, camera lenses come in many lengths and widths. So if you actually get into photography and start buying cameras, or you go watch people taking pictures, say at a sports event, they'll be working with these very long, heavy lenses often. On the other hand, people taking a panorama view of the whole, everything in front of them will actually have typically very small, short lenses. Many cameras have zoom lenses. So there are cameras that optically zoom in on the distant object, not digitally. Digital zoom means take the normal picture and just cut a chunk out of it and blow it up large. That's boring, that's computer work. But optical zoom means they actually project a larger pattern of light on the image sensor. And how do they pull that off? And then again, if you get into photography farther than to just snap and shoot, there are issues like what's called focal length and F number. And these affect the appearance of the pictures that you see. For things like if you want to go have a portrait of yourself taken, they will use a different lens typically than they would for taking a picture of scenery. And the difference has a lot to do with, F number choice actually matters here. And I can point out to you the differences and you go, oh yeah, I've seen that before. Okay, so the questions I'll go after, here's my list of 5, and the first is just the simplest of possible questions. Why do you need a lens at all? So let's start with that guy. I'll ask this anyway. The light ray is leaving one point on an object. So suppose you've got an object from which light is coming, and light is coming from all these objects on the front desk here right now because they're illuminated by other lights. So they're not producing light, at least that we can see. They're actually glowing in the infrared a little bit, but forget that. Light hits them, and we see that light, but I can make them brighter by just letting them emit light themselves. So you see those guys, and if we think about the light from one point on this long, hot filament, that's just a weird incandescent light bulb. The light from that point is spreading out in all directions. So some of it comes towards me, some of it goes towards you, every which way. If you want to take the light leaving that one point and bring it together and project it on one point on a screen or on an image sensor, so the image sensor says, at that location on that bulb I'm looking at, it's bright. What can you use to get the light to do that? The light diverging away from that point, heading in all directions, bring it back together, at least some of it at least, and project it right on that spot. So how many think you can use interference to do this? How about dispersion to do this? How about refraction to do this? Yeah. And polarization is not going to be, I won't even ask you. It's refraction. So lenses use refraction. We've already seen this. The bending of light as it goes through surfaces and changes speed. There are, I should say, and I used to teach about this, there are lenses that use reflection to do it. Mirrors. There are mirror lenses instead of refractive lenses. They're particularly useful for extreme telephoto lenses. And telescopes, most telescopes are basically mirror lenses. They're just gigantic mirror lenses. I can talk about mirror lenses if you care about it, but I'm going to focus on refractive lenses, which is the ones that are most common. So, in addressing this question, why does a camera need a lens? That if you look at the light that comes off of one surface, one object, and for the moment, let me just turn on that tall, thin lamp and turn off the others. Oops, of course, that's the one I don't want to turn off. I'll turn off the other guys. So just that lamp, and if I use no lens, I'll start with no lens here. The light from the top portion of that hot object, like the light from my little candle flame here, goes in all directions. In my drawing, I've only shown you a few directions that light can go. Of course, it goes in every which way. And some of it hits the screen, and if we look at the light pattern on the screen, I can look at it like this. Because it's a semi-transparent ground screen, we can look at it from the back also. So let me look at the back. And to do that, west, which I'll put it up here, up there. Okay, so you're now looking at the screen. And not surprisingly, it is actually seeing the light from that the glow, most of the glow you're seeing there originated in that light bulb filament. But you can't tell by looking at this screen. There's a slight ability to see that it's coming from that filament. But for the most part, it just looks like just a splash of light across that entire screen. No structure to it. It's not a photograph. You would be pretty disappointed if that was, the whole family out there smiling happily and it's just a blur. So without a lens, you get no structure to the pattern of light that hits the film or image sensor. The camera is struggling here, trying to find something to focus on because there's just sort of, it's all a big swash of nothing. It occasionally manages to figure out that there's a ground glass screen in front of it that it can find a little bit of structure in. All right? If you put a lens in there, though, surprise, and I got to focus. This is focusing here, right? Turns out I have to focus. I have to find the right distance between the lens and the image sensor, and voila, I get an image. And some details about this. First off, it's what's called a real image, meaning that I can put my hand in it. I can touch it. You can come up here. Ooh, I'm touching the image. And it will appear on my finger when I get in the way of it. So real images are ones you can put your hand in. You might think, well, what's the alternative? There are such things as virtual images. The virtual image is something you see with a magnifying glass. It's there, you see it, but you can't touch it. There's no place where that pattern of light sort of exists in space where your hand can go. I can talk about that later on. So this is a real image that's formed, and it means that any light that left the tip of this bulb where my finger is touching, that light, most of it went everywhere which way in the room, but a little bit of it went through a lens that's up here. The lens is about that big in diameter, so we're talking about gathering a tiny fraction of the light. We got all the light that goes through that image, that lens, that came from the tip of that filament. It all is brought back together and projected onto one spot here on the screen. That's the image formation process. You take light spraying out from one point on an object, and you bring it back and project it at one point on the image sensor. And other points on the object, their light sprays out, goes through the lens, and comes back to one point, a different point on the image sensor, and so on. You okay with that idea? So how does it manage to pull this trick off? So now we'll look at, I've got a board down here with a bunch of little laser beams, just as light sources. Document camera on the side. Yes, you're now looking down at a board with little laser beams. Actually, let me take out the lens initially. So no lens. So they're the little laser beams. They look kind of surreal for some reason on that screen, but they're real. I mean, I'm touching them and whatnot. And if you put a lens, if I put, do I have just a block? If I put just a block in the way, we see things we've seen before. The light bends toward the perpendicular when it slows down going into the block of plastic. So that's here. It bends toward the perpendicular. And then as it leaves, it bends away from the perpendicular. With just a block of transparent material that slows light down, you get a displacement in the beams. They were traveling over here. They were traveling along. This guy would have continued on here, but it's been pulled down. Actually, I'm clipping it. So let me not cut it off. Okay, there it is. It continues on. It's been displaced downward a little bit, but otherwise nothing much has happened. And this is why when you look through a window, you see the outside world essentially unchanged. There may be some tiny displacements, but who cares? But if these surfaces are not flat and they are not parallel to one another, you can get weird things that happen. They're, of course, very useful. like this. In this case, these beams, this beam that goes up here toward the top, it bends toward the perpendicular to that particular spot on this lens structure. So it bends, and as it leaves, it bends away from the perpendicular to this particular spot on the lens structure. And it turns out those two bends are in the same direction. It bends a little downward on entry, and it bends a little downward on exit. So it never goes back to its original direction, and it heads downward. On the other hand, this ray down here, and people talk about rays of light. This is what I'm going to talk about throughout this is what's called geometrical optics, ray optics, as opposed to what? As opposed to wave optics. We're going to treat light as just a beam of stuff. Don't worry about the fact that it's a wave. Wave optics is a whole other story, and it's mostly important with lasers, but it's not so useful to we will encounter it, but it's not useful for cameras, or important for cameras. So this ray down here bends up on entry because the surface is not the same. It's tilted differently than the surface at the top of the lens. So it bends up and it bends up again. So this ray is forever bent upward. And the ray that goes straight through the center drills straight into the flat surface. It's curved, but it is in this picture vertical. It goes straight and it doesn't bend at all because it was already perpendicular to the surface. And on exit, it doesn't bend at all because it was already perpendicular. So I think the name for these guys, having taught optics and quantum optics all these times in the past too, do I remember all the names? No. I think these are called the principal rays, but don't quote me on it. It's probably true. These three rays, one down low, bending up, one down, up high, bending down, and this one through the middle, going straight without any deviation. You can think of those are the principal rays, and in fact, they tell you sort of everything you need to know. They meet up. Having been bent toward each other, sooner or later, they're going to come together. What's not certain is, do they come together all at once, or do one pair come together first and the other ones later? Now, they all come together at once. What a nice coincidence. It's not perfect. They're pretty close to together at once. But this is a very simple lens structure. It's made with surfaces that, in this case, they're cut right out of a cylinder. That is, imagine a cylinder that's about that big, and just cut off the front face, and then take the back face that was over here on the wall, slice it up, and glue the two of them together. These are both pieces of the cylinder. It's a two-dimensional story. In a real lens, a three-dimensional version, this lens, this is a three-dimensional one now, this is cut from a sphere. So imagine a really big crystal ball, and you slice off just that edge on that side. And on the other one, you slice off just that edge and glue them together. You end up with this structure. And this is the three-dimensional version, the more useful version of that. So having done that then, having created this is a cylindrical lens, that's a spherical lens it's called. The rays do come together at almost one point together. It's not quite perfect. The failure of perfection is one of many shortcomings of overly simple lenses. So better lenses, typically groups of lenses working together as a team, can fix some of these minor problems and get you a better result. But the point here is that the rays coming from one direction all meet at one point. If they were coming differently, well, that's good enough. So that's what's happening here. Let me just leave that, and we'll look back at that camera that's over there, looking at the ground glass screen, and obtaining therefore an image of the light bulb filament. It's taking all the rays that come off the top tip of that light bulb filament, every one of them that goes through this lens, which is, it is a three-dimensional structure. It's not a cylinder. It's part of a sphere, and it is bending them all together and putting them all. They meet up right there. And the reason I had to focus is you saw they only meet at one location. Let me go back to this. I don't really mean to be obnoxious going back and forth. Look, if you look, we're now, come on, what did I do? Too many buttons. Side. There. Oh! Can't walk and chew gum at the same time. There we go. When I'm focusing, I'm moving the image sensor, the ground glass screen, back and forth. If I put the image sensor or the ground glass screen, basic equivalent, too close to the lens, the rays have sort of come together, but they haven't finished the job. And I get the light, all the light from one spot on the object hasn't met up yet. If I put it too far away from the lens, they've come apart already. Is that okay? So this is a way of looking at the focusing problem. And now if I go back to this, yeah, God, don't want to be a camera operator. If I put the ground glass screen, and instead of moving the ground glass screen, I'm going to move the lens. But it's the distance between the two that matters. But if I put the lens too close to the screen, the rays haven't come together yet. So they're coming together too late, after the screen's already gone. If I put the lens too far away from the screen, same problem. This, incidentally, everything I'm saying here about lenses and cameras is true of your eyes as well. So if the rays, because your eyes basically got a lens in it, just to point out, it's not just a lens. You know, there's a little lens-like structure inside your eye. There's also the front surface of the eyeball, the cornea. The cornea is actually part of the focusing process. You want that involved. This is one of the reasons why when you're, when you go swimming, it messes up your ability to focus because water's in contact with your cornea and changing its behavior. But anyway, if the lens / cornea of your eye are focusing the light and you want it to come into perfect into focus. You want the rays from that light over there to come together on one spot on your retina. If they come together before they hit your retina, you'll see it'll look fuzzy. If they come together after your retina, it'll look fuzzy. So what you're doing when you're focusing your eye, assuming you can pull it off, is you're trying to make sure that the rays come together right on the retina. And light from that spot comes to one spot on your retina. Light from that spot comes to a different one spot on your retina, and so on. You okay with that? Yeah.
How do glasses change the way that we focus, like reading glasses versus farsighted?
Great question. So Genesis' question is how do reading glasses affect the focus? And since this is our class, I can do anything I want with it, right? So we can play optician for a minute here. I'm going to come down and look at this guy again. I'll show you. If I can remember. Okay. Yeah, okay. So, suppose your retina, if your retina is right there and the lens is like that, everything came together just the right moment. Great, you see a sharp image. But what happens if, for some reason, your retina's here? Oh no, the light didn't come together on your retina. How are you going to fix that? Well, this is light, these light beams are actually, they're all traveling the same direction. That's the kind of light that originates from a very distant object, like the moon. Light from the moon is coming along. Any light that manages to get to your head has traveled almost exactly the same path, whether it hits the top of your head or the bottom of your head, because it started over there on some lunar crater, I don't know. The rays are amazingly parallel to one another. So this is light as though it originated from way, way far away. Can you follow that idea? If it originated in a candle, the rays that hit your head, this one will be hitting up, this one will be hitting down. They're fanning out. So this is just a special case. It's one case of light. It's light from a distant source, looks like this. And when it goes through this lens, it focuses too late on your retina. It looks fuzzy. You're looking at the moon, and the moon is fuzzy because the moon is coming into focus behind your retina. How do you fix this? Put on some glasses. And let's try this. This looks like here's some glasses. Helped a little bit. What I just added, this looks almost like a block. And that's why I'm picking it out very carefully. This is a set I've never played with, so it's kind of fun. It's a little bit of an extra lens. It has a little bit of, it's a little curved on the front. This is called convex, meaning that it's bowed out in the middle like a barrel. Convex is that shape. This is definitely convex. This guy's a little convex on the back side also. This is like reading glasses. Bad choice of thing. This is a converging lens, it's called. These are both converging lenses, meaning they take rays that are traveling parallel to one another and they bend them toward each other. And I'll show you in a minute the alternative. So this, we've put on glasses and it's a little better. What I want you to see, the rays hitting that Sharpie are a little closer together than they used to be. Can you see that? So if you are, yeah, I won't name this. Let me try a stronger lens. This is stronger. Here's another. Okay, oops, I overdid it. This is what you're doing when you're putting on glasses that are converging. And converging lenses make your eyes look bigger when someone looks at you. I'm not sure I've got one in between. Let me make it, if I make it really extreme like that, oh my gosh, you need Coke bottle lenses, right? There we go, fixed it. Okay, so if your retina is too close to the lens and you want to fix it, you put on thick converging lenses. Is that okay? Suppose the opposite is true, that instead of having your retina too close to the lens, it's too far from the lens. Well, now this is hardly going to help. That's the bad choice. So what do? You go to diverging lens. This is a diverging lens. It's curved the other way. And this makes your eyes look smaller when someone looks at you. You all can play with your own glasses and see whether they're converging or diverging. But this is the basic idea. You're adding an extra lens to help your main lens pitch the real image on your retina, not before or after your retina. So far, so good? To bring this into language that many of you would recognize, or you will 30 years from now, there are issues. Your lenses, amazing, are able to change their curvature. And that's true when you're in your 20s for sure. So that when you focus on something, you're actually changing how curved the lens in your eye is, and therefore where it pitches its real image. As you get older, you lose that accommodation. It's just inevitable. It's not like some shameful thing. It just happens because of the changing of the physiology of your eye. But the result is that people beyond a certain age sort of become kind of the focus doesn't change very much. They don't have a lot of control over where things focus, and people sort of settle down as either nearsighted or farsighted, or something in between. A person who is farsighted sees well at distance but has trouble focusing up close. And to give you an understanding of that, let me take a look not at just one of these light sources, but let me turn on all three again. So I'll build this story. I'll rebuild the story here for you all. We're going to look again at that image sensor. Oh, this is getting better at this, I think. Yeah, okay. All right. I can bring the nearest one, I'll bring that into focus. There it is. Okay, so now I have the long vertical filament sharply focused. These guys are too similar in distance. Let me pull that one farther back. I want them to be at different distances. But so the filament is as well focused as I can get it. But the tight spiral, the little compact fluorescence, is a fuzzball. Why? Because the light rays coming from it, do I have a, hell, I don't have a good picture for you. The light rays coming from the more distant compact fluorescent are traveling more parallel to one another when they hit the lens than the light rays from the closer vertical filament. As a result, the lens is able to focus the light rays from the distant source more easily than they can focus the light from the close source. Let me play hand waving to show you the difference. I'll imagine the lens here. I'm doing mind theater. Okay, so there's a lens here. If the source of light, or the object you're trying to focus on, is very close, the rays that hit it were spreading like crazy. They get through it. And it struggles to bend them back together. And it does bend them back together, but they don't actually come together until way over here. Okay? On the other hand, here's the lens again. Suppose this object that you care about is out here, which is much farther, of course. The rays that manage to go through that lens, the ones that were diverging like crazy, they don't make it. It's only the ones that were almost traveling together that make it to the lens. And so they enter the lens already pretty close, traveling almost the same direction, and the lens bends them toward each other by sort of the same increment, and they meet up here. So the nearer the object is to the lens, the farther away the image forms. Up to a point where there's actually a point when the object is too close to the lens, no image ever forms at all. And that's the minimum focus of your camera. You all have noticed with your camera that you can focus on, I don't know, with your cell phone, you can focus to here, but try as you like, you can't focus when it's an inch away from the camera. The rays are diverging too much. The lens of the camera just simply, no matter what it does, it can't bring them together. Is that okay with everybody? So this lens is doing a good job of bringing together the light from the nearby vertical filament because it's working hard to bend them. It brings them together here. The light from the more distant compact fluorescent is easier to bend together. It comes together too soon. It comes together about here before it gets to the screen, and it's already come apart again by the time it gets to the screen. If I want to make the compact fluorescent a sharper image, I need to move the screen and lens closer together, because the lens it's too easy for the lens to bring the rays together. They come together soon, nearer the lens. So if I move the lens toward the screen, there it is. That's as good a focus as I'm going to get. And now you'll notice that the rays from the vertical filament are out of focus. The lens is not able to bring those rays together on the screen. They come together after the screen, beyond the screen. You okay with this? Ask me questions if not. So this is what you're doing with focusing. You're picking, for a given distance, you're trying to make sure the rays from the objects at a certain distance come together right on the image sensor, not before or after it. And the cost is that rays coming from more distant objects or closer objects don't come together quite perfectly anymore. Is that okay with everybody? Before looking at solutions to this problem, let me go back to the eyeglasses story. So the eyeglasses story, do I want to do this? I can just do it by talking. Suppose you are far-sighted, which I think is the more common of the possibilities, meaning you see things at distance quite nicely, but stuff that's up close, you can't get into focus. You need reading glasses. What's going on there is that you can focus, your eye is capable of focusing those rays coming from far away and traveling almost the same direction. It focuses them right perfectly on your retina, great. But rays that come from nearby, your book, are spreading too much when they enter your eyes because there's too much, the angle possibilities are too wide. And your lens tries to focus them, but they do not come to focus by the time you get to your retina. They focus beyond your retina after it's over and done. So you need help focusing. You want the rays to bend together more tightly and meet up on your retina. So you wear glasses that are converging, that are like this guy, that bend the rays together. To show you that this actually is a converging lens, I should do this too. I'll take the rays that are coming from the ceiling lights, and I will bend them toward each other. There they are. Can you see the ceiling lights? So I'm converging them all together. You know, you actually get a pretty decent real image. Again, I can put my hand in it, it's real, of the ceiling lights. If I could get rid of the ceiling, I could do this with the sun, and we would get a circle, an image of the sun. It would be really bright and really hot, and you could burn things with it. So if you ever played with a magnifying glass burning stuff, you still do this? That's what you're doing. You're forming an image of the sun on whatever you're roasting, and it's so bright and hot that it just cooks stuff. Okay? So this would be the appropriate kind of lens for a person who's farsighted, who needs help bending the rays together to meet from a nearby object to bend the rays together on their retina. So far, so good? If you are nearsighted, so somebody whose eyes settle down, so this is all in focus, but they can't see at distance, their eyes are bending the rays too aggressively. They're able to bring together the tough to focus rays from the book, but they overdo it when they take the easy to focus rays coming from the moon. So they need something that helps them back off, take those rays and make them harder to focus. So they want a diverging lens, a lens that bends the rays apart from one another, and they enter your eye diverging more than before, and your eye then brings them together on your retina. Is it okay? So, you know, optometry school or something like that, or what else? Other thing to point out, I mentioned that if you put the object too close to a converging lens, the rays are diverging so badly from that object, that nearby object, that they don't come together at all. But they diverge differently than before. They were diverging like this, and now they've gone through the lens, the converging lens, and they diverge like this. They're still coming apart. They never come to a point. They never form a real image. But they look like they came from a more distant object. And the more distant object and a bigger object. And whereas this forms a real image of the overhead lights about 2 feet from it. If I brought stuff closer, can I do this? I'll get a more nearby. I'm not sure I can pull this off. I don't have enough room here. Yeah, I can't get an image. These guys are forming. They're all too close. I don't have enough. I could probably get it if I had a bigger room. But if you look here, this is not, the light now is not forming a real image. It's forming a virtual image that's back beyond the room. Do you see it? It should be here. You know, I'm supposed to start looking like a big goofball, right? This is a magnifying glass. Instead of forming a real image of me anywhere, it's forming a virtual image back here. So you're looking beyond me at an enlarged version of me. Is that okay? But it's all, you know, so it's all, lots of things, the games you can do with optics. Yeah, Jesse? What happens during cataract surgery? With the cataract, typically because of UV damage and things related, the actual lens in the eye becomes cloudier or worse or opaque. So when you take out that lens, so they take out the lens and they replace it with something that you know, a human-made conventional converging lens. So they're putting in a lens like this, although probably a tiny bit smaller, and typically flexible to get it in. They have to fold it and shove it in. And it's trying to replace the natural lens. So far, so good? A key difference is the natural lens that you all have. It's like this, but there are muscles around the outside that can change the diameter, in effect. And as they change the diameter of a flexible object, you can't just shrink it and have nothing happen. It's got a fixed volume because it's basically a liquid solid thing. So if you try to squeeze a baggie full of water or balloon full of water, if you try to make it thinner, it it swells in the other directions. On the other hand, if you try to shrink its diameter, it swells. Anyway, the same thing happens with the lenses in your eye. As you change the diameter of the physical lens, you change its curvature. It becomes more or less curved. Is that okay? And so that's how you focus. That's how you adjust. Instead of moving the distance between the lens and your retina, which is tough, you change the curvature of the lens. And that was the opening question I asked you. How do you make, changing the curvature of the lens changes how the image forms. So that's what you're doing. You're playing with the curvature of the lens. And I can show you that actually. This is a weakly curved lens here. And it forms, the images you're seeing right now, they're pretty big. If I use a less curved lens, that's a more highly curved lens. Here's a more highly curved lens. If I put it at the same location, fuzzball. But I have to move it much closer. Here's where it's in here. And I got to move it up. And I'm out of room. There, the images are here. They're not wonderfully clear, but they're much smaller, much brighter, and they form much closer to the lens because of the higher curvature. Is that okay? So as you change the curvature of the lens, several things happen. Do I want to try to disentangle? And I want to go back to your question about the cataracts. The curvature of the lens clearly matters. I'll get that better another time. But with cataract surgery, so first off is you're getting rid of the opacity of the existing lens. You're putting in a lens that is crystal clear and all, but it only has one curvature. You can't change the curvature anymore. So you have no ability to accommodate for objects at different distances.
Isn't that a bad thing?
Sure, you're giving something up. I have cataract surgery because I attribute it to my graduate school experience. I worked with a mercury vapor, a cell filled with mercury vapor for a long time doing laser studies of it. And it was made of a material that transmits ultraviolet. And who knew? Nobody told me. You're like roasting yourself. I don't ever remember getting sunburn from it, but man, it was not a good idea. So the effect of replacing the existing lenses, with people who will tell you that, and it's true, that suddenly you see colors properly again because the little particles that are developing as cataracts develop, Rayleigh scattering, right? They knock out the blues. The blues get scattered. They don't go through properly, right? So what's left is the reds and yellows. So the colors, the biggest effect, apart from just not being able to focus, getting a nice sharp image the way you want, is you lose the colors. And so the colors come back. You suddenly take out the Rayleigh scattering in particular, it's back to full color. Hey, this is great. Okay? You lose the focus. But in the modern era, eyeglasses are so good that they make eyeglasses that have different curvatures at different places in the eyeglasses, like these guys. These eyeglasses, I can see distance clear as a tack with the top of the glasses and up close perfectly with the bottom of the glasses. So it's good. Other questions? What else would I want to tell you before we leave here? Here's something worth saying. Let me go back to the longer lens. I hope it's somewhat convincing that, and I can make it more extreme. If I bring these guys to really different distances, you'll see you only get one in focus at a time, right? Because if I get the filament, the vertical filament in focus, the compact fluorescent is just a fuzzball. If I get the compact fluorescent in focus, the filament's a fuzzball. Is everybody okay with that? In part, that's because we're taking all the rays that hit that entire lens and trying to bring them together. And if we're off by even a small amount, they're not together and they come out all fuzzy, right? So like this. If the candle's at just the right distance to hit the image sensor, it's sharp. But if the candle or the image sensor are not at the right location relative to the lens, they're fuzzy. But if we only use the rays very close to the center of the lens, they're already so close together most of the trip that they're pretty sharp anyway. So what you can do is you can use an aperture. This is an aperture like from a fancy lens. Can you see it getting bigger, smaller? It's a whole bunch of leaves that bend in strategically so that they make a hole. It's a centimeter now. It's almost a pinhole now. Now it's wide open. If I put that in front of the lens, like this, and I force the lens to use only rays very near its middle, that's my goal. Right now I haven't shrunk the aperture. Here, now I'm going to shrink the aperture. When I do that, I get less light. That's a cost. But everything's in focus, in sharp focus. Because I'm only using those central rays, which are already very close together, and whether they're perfectly meeting up or almost meeting up, we're good. And this is why when it's very bright and the pupil of your eye is tiny, everything's in focus anyway. So if you have any focus problems at all, in a bright environment, you can read easily, you can see distance easily, everything's in focus. And furthermore, this is why people squint. They shrink the aperture, the effective aperture of their eyes. It's called an aperture. If you shrink the aperture of your eye, or you look through a pinhole, which you can make with your fingers, everything's sharp and focused, because you're only using those central rays. And the exact perfection of the lens and all that doesn't matter.